All right, let's start with a wild thought. You ever wonder if those bizarre, kind of mind-bending rules from the quantum world could actually show up in things we can see and touch? I know, it sounds like something straight out of a sci-fi movie, but that's exactly what we're digging into today, the 2025 Nobel Prize in Physics, which celebrates a discovery that brought all that quantum weirdness right into our world.
The Royal Swedish Academy of Sciences really nailed it with this quote. Their experiments on a chip revealed quantum physics in action. Just let that sink in for a second. We're talking about the strange rules that usually only govern tiny, invisible atoms, but seeing them happen in an object you could, in theory, hold in your hand. That's exactly what the Nobel Committee was celebrating here.
So, okay, what's the big deal? What does making quantum mechanics tangible actually mean for us? Well, this isn't just some abstract physics lecture. This is the origin story of a technological revolution that is happening right now, and it all traces back to one brilliant experiment.
This year's prize went to three scientists, John Clarke, Michel Devoret, and John Martinis, for some truly groundbreaking work they did way back in the 1980s at UC Berkeley. These are the guys who first kicked the door open.
You know, for the longest time, physicists basically saw two different universes. You had our everyday world, where everything is solid, predictable. And then you had the quantum world, of single particles, where things get, well, weird. What these scientists did was build a bridge between those two worlds. They showed that a large object, made of literally billions of atoms, could behave like one single atom. That line between the big and the small? Turns out it's not so solid after all.
And to really get why building that bridge is such a huge deal, we need to talk about just how different the rules are in those two worlds.
Okay, so let's paint a picture. In our normal, classical world, if you throw a tennis ball at a wall, it's going to bounce back every single time. It's predictable. But down in the quantum world, a tiny particle can sometimes just pass straight through a solid barrier, like a ghost. It's a world run on probability, not certainty. So naturally, this led to one of the biggest questions in all of physics. Could you actually build something big, something you can see and touch, that still plays by those spooky quantum rules? Could you bring that whole ghost-through-the-wall thing into our world? That was the challenge they took on.
Now, a discovery like this never just happens in a vacuum. It was really the peak of decades of research, building on earlier Nobel-winning ideas about superconductors. And then between 1984 and 1985, this team finally put all those puzzle pieces together in a series of just brilliant experiments.
And the key piece of their puzzle was this tiny little device called a Josephson junction. Here's how it works. You take two superconductors, these are materials where electricity flows with absolutely zero resistance, and you stick a super thin barrier between them. Now, all the normal rules of physics say that barrier should be a dead end for electricity, but a Josephson junction is like a secret tunnel to the quantum world. It lets the current do the impossible and pass right through.
Using this little quantum gateway, they made two discoveries that are honestly mind-bending. But don't worry, we can break them down with a couple of pretty simple analogies.
So first up, they saw that ghost-through-the-wall effect, but on a massive scale. It's called macroscopic quantum tunneling. We're not talking about one particle here. We're talking about billions of electrons in their circuit, all moving as a single team, and together they pass through an energy barrier that should have been a brick wall. It's like an entire army just phasing through a fortress. And their second discovery was just as wild. They found that the energy in their circuit was quantized. What on earth does that mean? Well, it means the system couldn't just have any random amount of energy. It could only exist at specific, fixed levels. Kind of like climbing a staircase. You can stand on the first step or the second step, but you can't just float in between them. And seeing energy behave like steps is a classic telltale sign that you're in the quantum world.
So, when you put it all together, what did they actually build? Something incredible. An artificial atom. Think about that. This was a thing made of metal and silicon on a chip, big enough to see. It had cables you could plug into and control, but it behaved exactly like a single tiny atom, complete with those weird energy steps. They had made a quantum system that they could actually control. And that little phrase, a controllable quantum system, that's everything. Because that idea is what turned a fundamental physics experiment into the blueprint for one of the most powerful technologies we can imagine, the quantum computer. See, their discovery led directly to the invention of the qubit, which is the absolute heart of any quantum computer. A normal computer bit is simple, right? It's either a 0 or a 1, on or off. But a qubit, because it's quantum, can be a 0, a 1, or, and here's the crazy part, both at the same time. It's a property called superposition. It's like a coin that's both heads and tails while it's spinning in the air. And being in multiple states at once is what gives quantum computers their almost unbelievable power.
So how does that energy staircase fit in? Well, that is the qubit. That artificial atom they built is the whole magic trick. The lowest energy step on their staircase is the 0 state. The next step up is the 1 state. By zapping it with just the right amount of energy, they could control whether it was a 0 or a 1. They had basically invented the fundamental hardware for the entire quantum age.
And this isn't just ancient history, folks. The laureates themselves are the ones who went on to build this future. John Martinis ended up leading the team that built Google's first truly powerful quantum computer. Michel Devoret is a chief scientist at Google Quantum AI. So their experiment from the 80s, it's the direct ancestor of the quantum processors being built right now by all the tech giants.
So what does all this mean for the rest of us in the real world? Well, this technology promises to solve problems that are literally impossible for today's best supercomputers. Take something like designing a new drug. That means simulating how incredibly complex molecules will interact, a problem so huge a supercomputer might take thousands of years to solve. A quantum computer could potentially do it in a matter of hours. We're talking about new medicines, hyper-efficient new materials, completely new ways of modeling our financial systems. The list goes on.
So when you look at it that way, the 2025 Nobel Prize wasn't just about celebrating a discovery from the past. It was about celebrating the moment we were handed the key to a whole new kind of future, the quantum future. Their experiment didn't just answer a deep question about the universe, it unlocked a door. And now the only question left is, what are we going to build on the other side?